write down the resulting crossing relations. We're equating these to expansions. But actually you run into an immediate problem with the numerical approach to the bootstrap that I just told you about, which is that this sigma, sigma, epsilon, epsilon OPE pulls in some OPE coefficient sigma, sigma O, and epsilon, epsilon O times some conformal block. But this has no obvious positivity properties. This could either be positive or negative. So we can't repeat this logic that used the fact that the coefficients of these blocks are so that's a difficulty with just analyzing this 4-point function. Now there's a way around it, which is to actually look at the whole system of 4-point functions containing both sigmas and epsilons. So if I combine with this sigma 4-point functions and epsilon 4-point functions, then I can write the system of crossing relations that you get using a matrix notation. And it looks something like lambda sigma sigma O, lambda epsilon epsilon O. So I'm going to put these together into a 2-vector. Then there's some call it F again. There's some 2x2 matrices. Which depend on U and V and could be related to the conformal blocks. And then on the other side I have lambda sigma sigma O and the epsilon epsilon O again. And actually, okay, there's not just one crossing relation, but there are, if you count out all the different bootstrap conditions you get from the system of correlators, there are 5 crossing relations. So this is actually a 5-vector of 2x2 matrices. Okay, so this part runs over the Z2 even operators. Okay, that can appear in sigma, sigma, epsilon, epsilon. Then there's another piece which runs over the Z2 odd operators and picks up coefficients like sigma, epsilon, O. And sorry, then there's another function F. Let's call this F plus and F minus, which appears here. Okay, so if I look at the system, the bootstrap equation is generalized to something of this form. Now that I've written things in terms of this 2x2 matrix structure, it's easier to see how to take advantage of the fact that I have the same OPE coefficients on this side and this side. So before that was just coded in a positivity property. Here there is also a positivity property, but it's a little more subtle. And what I can do is apply a functional to this F plus, which gives me a positive definite or positive semi-definite 2x2 matrix. Okay, so this positive semi-definite 2x2 matrix. And if the functional acting on this is a positive semi-definite matrix, it has eigenvalues which are either positive or 0. And so then if I diagonalize the matrix, then it turns into a sum of positive terms. So this is how I have to generalize the positivity condition. I also want alpha acting on this F minus be greater than or equal to 0 as well. So here again, you can see that necessarily we have to formulate things in terms of positive definite matrices, which again leads us to semi-definite programming. That's the approach we have to use. Okay, so now that we've done that generalization, I can show you the results from studying this system. So the first thing we have access to now is the spectrum of Z2 odd operators appearing in this sum. So we can try to place a bound on the dimension of sigma prime. Let's say as a function of the dimension of sigma. Now, we also have epsilon floating around as an external operator. And all the Bootstrap equations depend on the dimension of epsilon. So, so to actually make this into in general, there's some three-dimensional plot, but to make it a two-dimensional plot, let me assume that delta epsilon follows the bound on its value that we computed with the single correlator case. Okay, so we computed delta epsilon as a function of delta sigma, which looks like this. So I'm assuming delta epsilon follows this curve. And if you actually make this plot, so here, the icing value, what we see is that this goes like this, and actually right around the icing value it shoots up. And then a little bit after the icing value it shoots back down. You end up with a bound on the dimension that's a spike. Okay, so this is the disallowed region. And actually this is, okay, this is something 3. This shoots up to around 5. But what you can see is that, okay, this intuition that we had over here that maybe the icing model has a big gap in the Z2 spectrum seems to also be showing up in the Bootstrap. So only if you're in a narrow window around 0.518 are you allowed to decouple the sigma price. So we can also turn this around and say, let's assume that we want to impose a gap in the Z2 odd spectrum. So to be concrete, let me assume delta sigma prime is bigger than 3. So it's an irrelevant operator. Then, and replot the allowed region in the delta sigma, delta epsilon plane, which before gave me this upper bound. That. And now if I ask about the allowed region, well, you can see from this plot that imposing this gap in sigma prime will confine me to some window in delta sigma, at least if I'm following this curve. And we see that played out in this plot. So there's some closed allowed region around the icing point. And if you go farther enough in this direction, you also see some other allowed region over here. Where the precise shapes of these depends on the level of numerical precision that you push things to, or how many derivatives do I include in the search space of the function. Okay, so this is great. So we get some closed island around this point with this assumption. And we can also make it a little bit smaller by adding in an assumption like delta epsilon prime is bigger than 3. We want to input the number of relevant operators. One other piece of information that we can add that I didn't yet include over here is that the OPE coefficient sigma epsilon should be the same thing as the OPE coefficient sigma epsilon sigma. Okay, right. One of them appears here. One of them appears here. And you can impose the fact that they're equal to each other. And so, okay, so we've imposed all these relations, pushed the numerical precision of this to be very far. And we zoom in on this island over here. And okay, so you get some sequence of shrinking. Some sequence of shrinking islands. And this can be compared with the best Monte Carlo lattice studies that have been done, which give you some rectangle, some error bars of delta sigma and delta epsilon. And now the best bootstrap determinations, which would be this innermost island, are about a factor of 10 more precise than the Monte Carlo. Okay, so to give you a sense of the numbers, this is like 0.511, 5182. On this side, 1.4125. 1.413. Okay, so these are very, very precise determinations. Is this clear? What we've done? Okay, so as you might anticipate, this whole story can also be generalized to the ON vector models. This is something that we did earlier this year. And so let me go back to this plot delta phi versus delta S, where before I got some upper bounds with Kingson by considering a phi 4-point function. This is an ON fundamental. We can also add in constraints from these 4-point functions. So this is the leading ON singlet. And you see, okay, well, basically this whole story repeats itself. If I impose the condition that there's a gap in the ON fundamental channel. So if you think about the ON vector models, these are always in 4 minus epsilon dimensions. These are theories of n scalars with phi I squared interaction. And this leads to an equation of motion, which tells me that del squared phi I is related to phi I squared. So the whole story repeats itself. This tells me there should be a gap in the ON fundamental spectrum, and that's what we can put in to this plot. So if you like delta phi prime is bigger than 3. And it again leads to some sequence of islands for icing island, 2, 3, and so on.
So what about the big region? I mean, can you rule out also the? I mean, there is the small island.
Yes. Yes.
Can you rule out that part, or it is present? Yeah.
So so this region.
Or maybe it's not interesting, or you want to focus on the proximity.
So far we've focused on where we
see.
know these actual theories are. It would be very interesting to see if we could rule out this whole region. We haven't managed to do it yet.
I see.
And I also don't know if any other theories live in this region.
I mean, you don't have an example, you say.
I don't have an example of a theory that lives in this region. Also, I should say that this region seems to be more sensitive to how far we've pushed the numerics in terms of how many derivatives we've included in the.
So your intuition is that at the very end it would be possible to rule out.
that's right. So I would hope that it's possible to just rule out
I see.
this whole region. You know, ideally, you rule out this whole region up to delta sigma equals 3. Okay. So that you could say that the 3D IC model is the only Z2 symmetric 3D CFT with 2 relevant operators in it. So this would be sometimes in the critical phenomena context, people talk about universality.
Ah, okay.
This would be a rigorous way to establish universality. We haven't quite done that yet, but it might be that, you know, it might be that we need to include even more 4-point functions to push that to its completion.
Sorry, another stupid question. I mean, as far as you presented the material, it looks that there is no point to continue to use Monte Carlo with respect to Bootstrap. Is true, or there is some advantage of Monte Carlo with respect to Bootstrap in some other issue, or I don't know?
Well, so let me
Well, they're not limited to the conformal fixed point, right?
Sorry?
that's certainly true. So Monte Carlo can deviate from the conformal fixed point
Okay.
and ask many interesting questions
Okay.
there that we can't address.
So for this specific question, there is no point to use Monte Carlo, but
Well, so far what I told you looks like the whole story fits together, but there are also some confusing things that we've encountered in the Bootstrap, so it's very useful to have Monte Carlo
I see.
as a sanity check that what we're finding is real. So I'll give you some examples of that
Okay, thanks.
as well. Also, let me say that in the icing case, this is much better than Monte Carlo. Oh, was there a question?
I have a question just about the pocket region down there. So is there any simplification that, so it's the lower left-hand plot that you have?
Here?
Yeah. Is there any simplification which occurs in the, can you cut it off if delta sub sigma is very large? So in other words, could you derive an analytic bound on like nothing good happens out for delta sigma sufficiently large? So in other words, then you could potentially just grind out the entire thing numerically.
I don't know how to do that. I don't know how to derive an analytic bound, and we're also very far from the regime where delta sigma is large. So.
Well, yeah, I'm just saying, like, I mean, you could just say, like, well, no matter how good your computers get, you're never going to cover delta sigma, you know, to arbitrary values.
Yes.
So won't you eventually need an analytic bound of some kind to kind of kill off the entire region?
Well, as I said, I think the only thing we could hope to do is rule this out up to 3.
Yeah.
Because beyond 3 doesn't make sense because we made this assumption that delta sigma prime might start at 3. So that still might be tractable.
Mm-hmm. Yeah.
I mean, I think it would be great to also have an analytic bound at large dimensions, but I don't know how to do that in here. I also wanted to mention in these other cases, Monte Carlo is still better than the Bootstrap. So let me draw a zoom in on this O2 island. So this is delta phi, delta s, and okay, so far we've come up with some Bootstrap determination, like 1.505, 1.515. So it's roughly in the second digit. The best Monte Carlo is some rectangle over here. Also, as I said, for the O2 model, there are very precise helium-4 measurements. Actually, these were done aboard the space shuttle in the 90s because they wanted to get rid of the effects of gravity to make very precise measurements of the specific heat of helium-4. And those measurements measure a critical exponent connected to the heat capacity. This turns into a determination of delta S. But they don't have any sensitivity to delta phi. So that's some band which sits down here. And currently there's an 8 sigma discrepancy between the Monte Carlo and the helium-4 measurement. Unfortunately, this island goes through both of them right now. So, so this is actually a very concrete goal for the Bootstrap going forward, is to see if we can make this shrink enough to resolve this 8 sigma discrepancy.
What do the Monte Carlo people say about this?
Well, they think they did they don't think they did anything wrong.
Well, no duh.
And they have to do some estimates of their systematic error, but they seem to be pretty confident in these. I haven't dived into it enough to have a very strong opinion. But this has been essentially a mystery since the 90s. No one really knows what went wrong here.
Do you think that you have the possibility, the computational possibility to shrink more your island and say something about?
Yeah, I think so. There are various ways you can try to do it. You can just push to a larger search space for your functional. You can also include more 4-point functions. So we can include the 2-index tensor in the 4-point function. And so there's a lot of different ways we could push things further, and which is the best way, I'm not sure yet.
So it is realistic to think that you will be able to solve these debates, so to say.
I think so. Yeah, I'm optimistic. We really, we need basically a factor of 10.
I see.
To resolve this, and in this icing case, we've easily gotten that much by pushing things further. Okay. I'm still going till 10:30, right? Yeah. Or no, you don't. Sorry, 11. 11. Okay, great. Okay, but this whole story, we were able to make some contact with known theories. It all seems to hang together very nicely, and we've had some great successes. So now I want to talk about some other situations that we tried to do with Bootstrap, where we've gotten some more mysterious results. And they still need some more insights to properly interpret them. So there are 2 cases where we've seen some more mysterious results that I want to mention. One case is 4D, doing Bootstrap in 4 dimensions, and in particular for 4D n equals 1 CFTs. So I told you yesterday the 4D conformal blocks are known in terms of hypergeometric functions. Adding in supersymmetry requires a slight generalization of that story. So let me just say a little bit about how that works. So let's consider 4-point functions containing a scalar phi, where phi is a chiral operator. This phi being chiral means it's annihilated by the Q-bar supercharge. And now that once we're thinking about this 4-point function, we can now expand it in the different OPE. So I can either expand into the phi dagger phi OPE, giving me a sum over non-chiral unprotected operators, or I can expand it in, say, the phi phi OPE, the chiral OPE. Or I should say I can also expand it in this way, which gives me a different expansion of the chiral OPE. So this leads to some system of Bootstrap equations. unprotected operator O, where dimension of O satisfies the unitarity bound. Delta is greater than L plus B minus 2. And because we have supersymmetry, we know that O sits inside of a supersymmetry multiplet. And so it comes together with various superdescendants. Which can be organized into primary operators under the conformal group. So let's project these onto their primary components. And because of supersymmetry, all of the OPE coefficients of these operators are related to each other. Okay? So this means that if I look at the contributions of this whole multiplet, it gives me some finite sum of conformal blocks with relative coefficients that you can calculate, and they're fixed by supersymmetry. So this whole contribution is what you might call a superconformal block. Okay, so this expansion will be an expansion in superconformal blocks. We can also, as I said, expand things in the phi OPE. And what does this OPE look like? Well, first of all, I can get a chiral phi squared operator. I can also get other things that are annihilated by Q bar. Okay, so the constraint here is that the left-hand side is annihilated by Q bar, so whatever appears on the right has to be annihilated by Q bar. And actually, there are different types of operators that satisfy this property. So, for example, if I have some non-chiral operator O, and I take its Q bar squared descendant, then this is annihilated by Q bar, because Q bar cubed is 0. Okay, so this, okay, for the n equals 1 theories have a U1R symmetry. The U1R charge of phi is related to its scaling dimension. And so this also fixes the U1R charge of O. And so there's some unitarity bound of the dimension of O that's determined in terms of this U1R charge that you could write down. So in this case, this operator has to have a dimension bigger than Q delta phi plus minus 3 plus L plus 3. There are also operators of this type with one Q bar acting on O. And in general, okay, something of this form won't be annihilated by Q bar, but there are certain protected operators that satisfy a BPS condition such that this combination will be annihilated by Q bar. So I probably don't have time to go through that in great detail, but because they're protected operators, their dimensions are fixed. The dimension of this object is 2 delta phi plus L. I should say the dimension of this object is 2 delta phi. And these types of operators only exist for L greater than 0. So there's a sense in which these are higher spin extensions of phi squared. So this is the general form of the phi-phi OPE. If you want to rigorously